This video will show how to calculate the energy loss due to conduction through three materials: wood, styrofoam, and aluminum. So we're going to talk about not all of a house, but just the walls of a house. We're not including doors or windows or the roof, just the four walls. And you can extend this on your own to other parts of a house. But I have a drawing here of the four walls of a house. Each wall is 7 meters long and 3 meters high, and the walls are all going to have a uniform thickness of 4 centimeters. I'm selecting to have the inside of the house at 68 degrees Fahrenheit and the outside of the house at 10 degrees Fahrenheit. So it's a Midwest type calculation in the Northern Hemisphere in winter. So we want to determine how much energy passes through the walls in 1 hour. And we'll do that for one material, and then we'll show the calculation for the other two materials. Our basic relationship here, simple approximation to this energy loss through the wall, is going to be a constant K that depends on what the wall is made of, the area involved, the amount of time that passes, and how much temperature difference there is from the outside and inside, and then divide by the thickness of the wall. So I looked up in a book and found that the constant for wood that we'll use here in place of K is that there's a range, but I picked about the middle of the range, is 0.1 joules per second per meter per degree Celsius. Now, you see the degrees Celsius here, so in the problem, it's obvious that we have to do some changing. We're given the Fahrenheit temperature, but we need Celsius. So the way we handle that is the temperature inside in Celsius is going to be 5/9 of the quantity, 68 minus 32. That's 20 degrees Celsius. Same conversion for the 10 degree Fahrenheit temperature. Now in the Celsius, we're at a negative number, minus 12.2 degrees Celsius. We're below the freezing point of water. So let's do this calculation for wood, and we're doing this for 1 hour. So we put in the constant, you can see its units. We have 4 walls. Each wall has an area of 21 square meters, so 4 times the area of one wall. And then the time we're doing this is 3,600 seconds. If you notice, our constant here, the K, is per second. And then the temperature difference, 20 degrees on the inside, minus 12.2 degrees Celsius on the outside. The temperature difference is 32.2 degrees Celsius. We convert centimeters to meters. And you should probably pause the video, do this calculation. Welcome back. And what I found is that the Q, the energy passing through these 4 walls in 1 hour, is 2.43 times 10 to the 7th joules. And just for interest, I wanted to convert that into BTUs. And this is for 1 hour. 9.48 10 to the minus 4 BTUs is 1 joule. So I get about 23,000 BTUs. About 23,000 BTUs is the energy passing through the 4 walls. And you know, this is in the ballpark. It's in the range. A furnace in the Midwest might be rated at 50,000 BTUs per hour. And this calculation is showing an energy loss of 23,000 BTUs. So that's for wood. How would we calculate for styrofoam? Would we go through all these steps and repeat the calculation? Well, it's not necessary. We can just find the constant for styrofoam, and that turns out to be 0.01 joules per second per meter per degree Celsius. And by the way, you should convince yourself that the units canceled appropriately up here. And I found a Q of 23,000 BTUs, the wood number, times the K for the styrofoam divided by the K for the wood. And you can readily understand we're getting 2,308 instead of 23,000. the K number is 10 times smaller. So if the K number is 10 times smaller, the Q number is going to be 10 times smaller if everything else is equal, and that's what I'm claiming here. The walls are now pure styrofoam, no wood, or all styrofoam. What about the aluminum? Well, the aluminum has a higher, much higher K value. The aluminum is 220. So I start with the value for wood for the Q. I multiply by the K for the aluminum. I divide by the K for the wood. And we find 5.08 times 10 to the 7th BTUs. This is why homes do not have walls of solid aluminum. The energy loss is significant. And just compared to the wood is 0.1, this is 220. So the ratio of the K, the thermal conductivity here, is over 2,000 higher for the aluminum. Which conducts electricity better, aluminum or wood? It's the aluminum, of course, and there's a common reason. It's not all of the explanation, but for a metal, roughly each atom has one more or less free electron, an electron that can travel through the material without much resistance. Wood is an insulator, and the electrons in each atom are bound. For the case of a metal where the electrons are free to roam, the electrons can carry kinetic energy much more easily from neighbor to neighbor and leads to a higher conductivity. So there's an example of calculating energy loss due to conduction. There's a formula that you have to look up the K value for the material, determine what the area is that the energy is moving through, how much time is involved, the change in temperature in Celsius from one side of the barrier to the other, and the thickness of the barrier in meters. If you'd like more physics and astronomy tutorial videos, those are my two websites. It's free. There's no registration required. At these websites, you'll find a list of videos, a description of the videos. If you enjoy these videos, please subscribe to my channel on YouTube. Ask your instructor questions.